In the last video, we discussed some integration techniques that can be used where for complex radical expressions or expressions with powers in the denominator, you can do substitutions with trigonometric functions. And in order to understand this video, you should probably watch that last video. But in this video, I'm just going to do a couple of examples. So for the first one, let's start with, so right off the bat, we look at under the radical and we see we have a 25 minus x squared. And this corresponds to a sign substitution. And so for my x, I'm going to sub in my a is not 25, my a is 5 because we have 5 squared to get 25. So I'll have my x be equal to x equals 5 sine theta. And that means that my dx, for when we decide to do our substitution, is going to be so now with my substitution, I can rewrite this entire expression as my dx, is just going to be 5 cosine d theta. So I just subbed out my dx there. Now I'm going to sub in my x. So we're going to get 25 minus, my x is 5 sine theta. Just like that. Now I'm going to change colors and I am going to do the integration with respect to theta. So we're going to get 5 cosine theta. And I'm going to first apply this square. So I'm going to get 25 minus 25 sine squared theta. And I'm going to draw out a 25. So to verify this, you can go through and do this step yourself. But once we have this form, 1 minus sine squared theta, according to Pythagorean's trigonometric identity, is just equal to cosine squared theta. So we can rewrite this expression as, now, the square root of the product of two squares is just the absolute value of those two numbers. So we can simplify this expression as 5 cosine theta over 5 cosine theta. That just becomes 1. And so we get the integral of 1 with respect to theta equals theta. Now we have to sub back in our substitution of x. X equals 5 sine theta. In order to get this in terms of theta, we have to divide by 5 on both sides, which we're going to have x over 5 equals sine theta, and then take the arctangent, or the inverse tangent, inverse sine of both sides. So that's going to be our theta, and you can verify that for yourself. So our final integral, will just be arc sine of x over 5 plus c, and that's our final integral solved. Now let's do an example involving tangent. Now we know that this one involves tangent because it takes the form of x squared plus a squared, Our a squared here is just 2 squared, because 2 squared is 4. And so we can do a substitution of x equals a, remember our a is 2, of 2 times tangent theta, which makes our dx equal to 2 secant squared theta d theta. This is just a standard derivative that you should know. And now we're going to sub these in, and I'm going to do it in a different color to show that we are integrating with respect to theta. So we're going to go and now I can distribute that squared, and rewrite this as the next step in solving this would be to take out a 4 so that we can get this as the product of two functions, and you'll see how we get that. So we have our secant squared over the square root of 4 times 1, This is 4 times 1 plus tan squared theta. And I'm not going to write 1 plus tan squared theta, because you should know that 1 plus tan squared theta is equal to secant squared theta according to the Pythagorean trigonometric identities. So we're just going to get 4 times secant squared theta. And now we apply our square root of the product of two squares rule, and we are going to be able to simplify this as 2 secant squared theta over 2 secant theta d theta, just like that. Now one of these secants is going to cancel out with the one in the denominator, and these 2's are going to cancel out, and our final integral, right, with respect to theta is going to be secant theta d theta. If you have watched about 2 videos ago, you will have seen how to integrate secant theta, and this is just a standard integral, so I'm not going to integrate it here, but the integral of secant x, or secant anything, is just going to be the natural log, right, of secant plus tangent. Alright, and this is our final integral with respect to theta, but we're not done because we haven't replaced our thetas here, because we want to have our integral with respect to x. The very first thing, tangent theta, was conveniently close to our substitution, right? We can rewrite this as tangent theta equals x half. So this whole tangent theta can be replaced with an x half. But my secant theta is a little bit more tricky. We know that for a given triangle, and we'll go up to our, because we're doing a tangent substitution, we'll go up to our tangent triangle over here as an example, that secant theta is just going to be equal to the hypotenuse, or this one right here, over the adjacent, or this one right here. And our hypotenuse, right, if we drew our triangle here, and if we wanted to find the secant of theta, right, given that this was our theta, we would take the hypotenuse over the adjacent. So when we sub our secant back in, right, for the hypotenuse over the adjacent, our final integral in terms of x, our very final integral, will be the ln absolute value of, just like that, and that's our final integral. Now we're going to do one last example, but for secant. Now, this particular example that I chose is a little bit more tricky because we don't have our radical in the denominator, but instead in the numerator. However, we still can do a trigonometric substitution because we have this form of x squared minus 9, which corresponds to our secant substitution. So we can use an x equal to, right, there's our a, 3 secant theta, just like that. And that means that our dx is going to be equal to 3 secant theta tangent theta d theta, right? This derivative of secant theta is just a standard, which is secant theta tangent theta. And now I'm going to do my substitution. Right, so all I did was I subbed in my x's here, and then I subbed in my dx, so that I got 3 secant theta tan theta d theta. Okay, and now I'm going to simplify. First off, this 3 secant theta, right, can cancel with that 3 secant theta. And then I'm going to simplify this inside expression, right? So this just inside the radical. I'm not thinking about the radical right now, but I can distribute that squared and get 9 secant squared theta, right, minus 9. So all I did was I distributed this squared into the parentheses there. And then I can draw out a 9. And I can get 9 times secant squared theta minus 1. Okay? And secant squared theta minus 1, according to the Pythagorean trigonometric identities, is just tangent squared theta. So this entire expression, in terms of theta, can be rewritten as the square root of 9 tangent squared theta, right, over 1, because that 3 secant theta and that 3 secant theta got canceled out, times tangent theta d theta, just like that. And this can be rewritten as the integral of 3 tangent squared theta d theta, right? So all I did was I used my square root of the product of squares rule, and I got a 3 here, and I got a tangent theta there. So I got 3 tan theta d theta, and then I just multiply those tan thetas together to get 3 tan squared theta d theta. Now, there's this little trick that we have to use because there's no standard integral or anything, no convenient substitution that can be used for a tangent squared theta here. So what we have to do is we have to write this as 3 times secant squared theta minus 1, right? d theta. According to Pythagorean's identity, that is a truth. And now we're going to be able to write this as 3 times the integral of secant squared theta minus 3 times the integral of 1. And both of these are with respect, right, to d theta. And, you know, all I did was I distributed that 3, so I got 3 secant squared theta minus 3. And then I split up the fractions about this negative. And we know that the integral of secant squared theta is just tangent theta. That's a standard integral. So we're going to get 3 tan theta minus, and the integral of 1 is just theta, 3 theta. Now we have to sub back in for our x's. And I'm going to kind of clean this up a little bit. So now we need to sub back in our x, because we want this integral in terms of x, and we've only found the integral in terms of theta. So let's work with the tangent theta right now. If we drew our triangle, so the tangent of theta is equivalent to the opposite, which is this x squared minus 9, the square root, over the adjacent, which is 3. So our tangent theta can just be rewritten in terms of x as 3 times, and actually I'm going to get rid of this 3. So it's going to be rewritten as just the square root of x squared minus 9. And the reason why it's just the square root of x squared minus 9 is because tangent theta is x squared minus 9 over 3. And this 3 and that 3 cancel out to just leave us with an x squared minus 9. And then we're going to go minus 3 times theta. And I'm just going to do a arcsecant property based on the x that we substituted. So the theta, okay, so assuming that our x is equal to 3 secant theta, right? X over 3 is going to be equal to secant theta, which means that theta is just going to be equal to, right, arcsecant of x over 3. And now I can sub that back in for my theta, and I'm going to get my final integral, right, in terms of x is equal to x squared minus 9 minus 3 arcsecant x over 3. And that's the final integral